In this video, we'll be talking about option C, energy, nuclear fusion, and fission. The first concept that we'll be discussing about is nuclear binding energy, which is the energy required to split an atom's nucleus into protons and neutrons, or it can also be understood as the energy released when protons and neutrons come together to form the nucleus. And if we take the binding energy for a nucleus and divide it by the total number of nucleons, we'll get the average binding energy per nucleon, which is also a measure of the stability of the nucleus. And the greater the binding energy per nucleon, the more stable the nucleus will be. The main concept of this whole lesson is nuclear fusion, which is the joining together of smaller nuclei to make a larger one and release energy in the process. An example of a nuclear fusion reaction is the one that takes place in the sun, which is the fusion of hydrogen nuclei that is the main source of the sun's energy. Here we can see two isotopes of hydrogen, deuterium and tritium, under very high pressure will undergo nuclear fusion to produce helium, neutron, and energy. The average binding energy per nucleon of the product, which is the helium, will be greater than that of the reactant, which is hydrogen. Now we'll be looking at a nuclear reaction for the fusion of deuterium and tritium to form helium and neutron. And nuclear equations must be balanced, therefore the sum of the mass number and the atomic number must be the same on both sides of the equation. Now we'll be looking at the atomic absorption spectrum of the sun. Since the sun has a sufficiently high temperature, it will give out a continuous spectrum of all wavelengths in the visible light. As the light passes through the cooler gases, such as helium and hydrogen in the outer atmosphere of the sun, certain wavelengths are absorbed by those cooler gases, and this produces the black lines in the absorption spectrum. Since each element has a unique absorption spectrum, the elemental composition of the stars can be determined by comparing the absorption spectrum of the star to the absorption spectrum of the known element. Next, we'll be looking at the atomic absorption spectra of hydrogen. Here we can see that the lines in the emission spectrum of hydrogen are caused by electrons falling down from a higher energy level to level 2, during which electrons will emit energy that corresponds to the wavelength of visible light. In the absorption spectrum, the lines are caused by energy being absorbed to promote electrons from level 2 to a higher energy level. The next important concept in C.3 is nuclear fission, which is when the large unstable nuclei break down to smaller, more stable nuclei, releasing energy in the process. In this process, average binding energy per nucleon of the product is higher than the reactant. An example of nuclear fission is the fission of uranium-235, where we have one bombarded with neutrons. Uranium-235 will absorb one neutron to produce the highly unstable uranium-236, in which it will break apart into two smaller nuclei and more neutrons, which also release energy in the process. And now we will have a nuclear equation for the fission reaction of uranium-235. In addition to the two more stable nuclei, the fission reaction also produces 3 more neutrons, which are used to initiate a chain reaction. And here we can see that in a nuclear reactor, the 3 neutrons produced in each fission of uranium-235 will go on to collide with other uranium-235 nuclei to initiate a self-sustaining chain reaction, which we can see in this diagram right here. However, some of the neutrons produced in a fission reaction will escape from the uranium sample without causing further fission. Therefore, there must be a sufficient mass of uranium present so that enough neutrons will cause fission reaction before escaping from the reactor core. And this is called the critical mass, which is the mass of uranium needed in order for the reaction to become self-sustaining. However, if too many neutrons cause fission, the chain reaction could go out of control that cause very bad consequences. Therefore, control rods are put in use to prevent too many neutrons cause fission. Next up, we'll be having a look at breeder reactor, which is a nuclear reactor that generates more fissile materials than it consumes. A fissile material is a material that is capable of sustaining a nuclear chain reaction. So why do we need breeder reactors? We need breeder reactor because the supply of fissile uranium-235 is limited, and therefore breeder reactors were developed to increase the amount of fissionable nuclear fuel available. We'll now have a look at the nuclear reactions that occur in a breeder reactor. The first nuclear reaction is a neutron capture, in which uranium-238 absorbs a neutron to form the heavier uranium-239. Next, uranium-239 undergoes a beta- decay where a beta particle is emitted to form the neptunium-239. Neptunium-239 further decays to form plutonium-239, which is a fissile material with the emission of another beta particle. Finally, plutonium-239 is bombarded with a neutron and undergo nuclear fission. The products are barium-145, strontium-93, and 2 neutrons. We'll now be looking at the comparison between the use of nuclear fusion and nuclear fission. Nuclear fusion has the potential to provide an almost unlimited source of energy. The fuel is inexpensive and abundant, and no radioactive waste is produced. However, there is currently no working nuclear fusion power plant on Earth, meaning that the use of nuclear fusion is not yet a viable source of energy. Nuclear fission can be used to generate electricity in a nuclear power station. Nuclear power stations have low greenhouse gas emissions. However, a disadvantage of the use of nuclear fission is that it produces radioactive waste, and the nuclear accidents that happened in Chernobyl in 1986 and Fukushima in 2011 has also highlighted many risks involved in the use of nuclear fission. Both nuclear fusion and nuclear fission can be used to create nuclear weapons. Another disadvantage of the use of nuclear waste include the radioactive waste that is produced, and the classification of them is important in determining the appropriate disposal and safety measures. Low-level nuclear waste includes items such as gloves or protective clothing that have been exposed to radioactivity. They have short half-life and low radioactivity, however, they are produced in high volumes. They can be stored as in cooling ponds until the radioactivity has fallen to safe levels, or they can also be incinerated or buried underground. High-level nuclear waste include spent fuel rods and waste from the reprocessing of the spent nuclear fuel. They will have long half-lives, high radioactivity, however, they are produced in low volume. They can be stored as in reprocessing for further use, or they can also go through a process called vitrification, in which they're converted into solid glass, and then they will be stored in stainless steel containers and buried underground in geologically stable locations. The last topic to be covered today is half-life, which is the time taken for half of the radioactive nuclei in a sample to undergo radioactive decay. Or in other words, it is the time taken for the radioactive nuclei present in the sample to have its original value. Here in the right, we're having a graph that is illustrating the exponential decay of a radioisotope with a half-life of 2 seconds, meaning that it takes 2 seconds for the number of radioactive nuclei to decay to half of its original value. We can see that in the beginning, we're having 8 radioactive nuclei, and it takes 2 seconds for them to half of their original value and become 4 radioactive nuclei. Similarly, it takes another 2 seconds for 4 radioactive nuclei to half of its original value and become 2 radioactive nuclei. So that's it for today, and thank you so much for watching. These are the summary of nuclear fusion and nuclear fission, so please pause the video to read them and make sure that you can address everything. Thank you.